The Large Hadron Collider is used to collide particles at almost the speed of light, and from the collision, there may result some particles that we may not have discovered yet. But how do we get particles accelerate at such high speeds? To do that, we may first consider a hydrogen atom which has a proton in its nucleus and an electron orbiting around it. And if we remove the electron, what's left behind is the proton. And imagine we have a stream of protons like that. And from that stream of proton, how do we get it to accelerate? Since proton is positively charged and charged particle will accelerate in an electric field, so if we put the protons in an electric field, the proton will accelerate along it, and the proton will go away from the positively charged end towards the negatively charged end. And when the stream of proton reaches the negatively charged end, we can continue accelerating them by continue the electric field. And as we continue that electric field, which forms a chain of electric fields that can accelerate the stream of protons to extremely high speeds. But the distance it gets when the proton is accelerated from rest to very high speed is increasingly large. As the more electric field we experience the proton in, the faster it can go. So the longer the chain becomes. But in the real world, we do not have such long distance on land, so we can only accelerate the stream of protons in a train like this along a certain distance. After that distance, we can accelerate it in a more effective way. If you imagine that chain of electric field wraps around on itself and connecting both ends, what we get is a circle. And if we draw the circle, and we put a section of electric field inside the circle, and this loops around until it gets back to itself. So the stream of proton inside that circle will keep accelerating at very high speeds. But you may think that, but since the stream of proton is in a circular motion, and circular motion have an tangential force which is provided by the electric field on the circle, and also a centripetal force, which is the force towards the center of the circle. What could that force be provided from? And usually there is electric, and along beside the electric we have a magnetic field, and that magnetic field is perpendicular to the electric field, which is what we want. And as you can see, the tangential force is provided by the electric field, and the centripetal force is provided from the magnetic field, and those two forces combined will make the stream of proton in a circular motion. So how do we provide that magnetic field? The electric field can be generated from two oppositely charged planes, and the magnetic field, if you remember, in a circular loop of currents, there is electron traveling along this circular path, and moving charges produces a magnetic field which wraps around it. This is a perpendicular circle which just wraps around the path that the electron moves. If the electron moves in a straight line, then the path of the magnetic field is circular around it. So we apply that to a circular loop of currents, and if we sum all those little circular paths up, and what we get is an magnetic field, which you can see as an magnetic field generated from a circular current. And back to this, we now know how the magnetic field is generated. It's by a loop of currents that flows through it, and that loop of currents will generate a magnetic field. and the magnetic force is perpendicular to the electric force. So that's why if we put a loop of current besides the electric field, the stream of electrons, the streams of protons will experience both the tangential force from the electric field and the magnetic force from the loop of currents, which generates a magnetic field towards the center of the circle. And that stream of proton will travel in a circular motion. But when the protons traveling at near the speed of light, the currents required to generate the magnetic force, which is also the centripetal force, to keep the protons traveling inside a circular fixed radius. And the current will increase exponentially to beyond what we can generate in normal conditions, which contains air particles. So what we need to do is to put that loop of currents inside a vacuum, and also the protons are traveling in the vacuum as well, and the vacuum has no air particles that resist the motion of the protons and the electrons in a loop of current. So this way, the speed that the proton can travel can be even faster, since there is no air resistance, and the loop of currents can be larger, which means the magnetic field is that the loop of current generates can also be larger, so the centripetal force can also be increased, and therefore we can generate enough centripetal force to keep the stream of protons in a circular motion. But when traveling at near the speed of light, there is also another effect we need to consider, which is the special relativity, and it causes the protons to become more massive as their speed increases, and the stream of protons, when observed from rest, their length will be contracted. So these are the two effects that come into play when the protons are traveling at near the speed of light. How can we make the protons travel even faster, if you may ask? If you remember, the acceleration in a circular motion is proportional to square of the velocity, but inversely proportional to the radius of the circle. That means the speed on a circular motion, the velocity is proportional to the acceleration and the radius of the circle. And if you want to see why, here's the formulas. We rearrange that to get the velocity is equal to the square root of the acceleration times the radius of the circle, and the acceleration is generated from the electric field, which the electric field may have some limit to the force that it can generate. Assume it has a maximum force that the electric field can generate. That means for a fixed mass of proton, there is also a maximum acceleration that it can reach. So when the protons reaches that maximum acceleration, then the acceleration becomes a constant. But what about the radius? The radius is what we can increase in order to increase the velocity. So going back to our loop, this loop may have a certain maximum velocity since its radius is fixed, and the maximum acceleration that the electric field can provide is also limited. So if the protons keep traveling along this loop, it will eventually reach a certain speed, and it cannot become faster anymore. In order to accelerate faster or traveling faster, what we need is a bigger loop. Let me illustrate that here. If we imagine the stream of proton will be traveling along along a extremely large loop, which is drawn here. So the stream of protons, when it reaches its terminal speed at the small loop down here, that means its speed no longer increase anymore. Then we can put the protons inside this loop for it to travel faster, as the radius of this loop is much larger than the previous loop. So the stream of protons can travel at a much higher speed than it previously could. And so the protons will accelerate even faster, and at this loop the protons will accelerate at almost the speed of light, extremely close to that. So the protons will become concentrated together as length contraction effect becomes much stronger, and the mass of the proton will also be much more massive than it previously had. So this is the loop that can make the proton travel at extremely high speed, but we not only want the proton to travel at high speed, we also want to see how would those protons traveling at such high speed when collided together, and like a block of matter colliding with another block of matter in a very high speed, the components of the matter will come out, as the energy of the collision between the matters are high enough to separate the bonds inside that matter. So we can explore what is inside a matter by colliding them together. That is the same case here. What we can do is put those extremely high speed protons on an even larger loop than before, and the loop may be this large, which is this large, and when the proton is traveling inside this loop, and as in any loop, there is a maximum speed that it can reach, as the reason presented as before. So when the maximum speed is reached in this loop, the protons will be put on an even larger loop. That means it will come out here and also here in opposite direction, so that around the loop they will smash into each other. They will colliding at this point. And what happens when two extremely high-speed protons colliding together is the energy from the collision will produce matter from energy, as in this equation, which you may also recognize. This is the mass energy equation that Einstein derived, and this equation says energy can be converted into mass, but when only a small portion of it can. So when the collision happens here, there are lots of energy releases in all directions, and the energy releases can be converted into mass. That means there could be some new particles forming, and we may be able to discover those particles if we have some detectors that detect a particle when that particle hit the detector. And that is what is actually doing in the collider, is at each point of collision, the point of collision also have a lot of detectors that can detect particles result from the collision, and the detectors can detect different types of particles. For example, some normal matter is made up of protons and neutrons and electrons, and the detectors can detect the trace of those particles, but there are also some particles that the detectors may not be able to detect. For example, some subatomic particles or elementary particles that make up the atom. For example, an electron is an elementary particle, since we do not know anything smaller than that. And proton is not an elementary particle, as it is made up of even smaller particles such as quark, and other things. Those are elementary particles, which is the smallest thing we know to date. And there were some elementary particles that don't behave like normal matter would. For example, some normal matter would have mass, but some don't have mass. Some elementary particles do not have mass. So, for example, light is an elementary particle of photon, and photons do not have mass. So light can travel at the speed of light. But there are also some particles that can travel at that speed. Those particles are neutrinos. The neutrinos also have no mass, and they almost not interact with anything. Unlike normal particles interact with other particles, neutrino is not as active as other particles were. So to detect them, we may need a special detector in order to detect them. And you may wonder what the collider, such a large collider, do if it can only smash particles together, and what result we actually get from the collider. And not far ago, almost 10 years ago, the Large Hadron Collider actually discovered a new particle, which is predicted by the standard model, which is the most accurate model in physics today. And that model predicts there is a particle which can generate a field. That field can give other particles mass, and like the electric field that the particles with charge would generate, the mass field, or it is called the Higgs field, which this field gives mass to particles that we know. And those don't have mass, such as photon or neutrino, do not interact with that field. So mass is a property of object like charges is also a property of a particle, and neutrons don't have any charges, so it don't interact with the electric field, same as the photon. And this is the first time that the Large Hadron Collider have proved its existence is useful to physics and other science, natural science, since it can discover some elementary particles which was predicted by some physics model before, and test that model to see if the model was correct. And if it is correct, it will detect some particles which is predicted by the model. And after we discover the Higgs particle, which give mass to other things, what can we discover more? And there are some particles or some questions we want to answer related to the universe that we may not have the correct physics model to answer it. For example, the movement of galaxies, which the galaxy assumed to be rotated around a central black hole, and the speed at which the galaxy revolves around is predicted by the current model to be slower, to be much slower to what is actually observed. Since if the observed result was correct, since if the model is correct, then we wouldn't have observed what we have observed. The speed of galaxy is moving right now. And some physicists hypothesize there could be some matter that could not be detected by any instrument we know of, and the particle and those matter will have mass that we cannot see. So those are called dark matter, since we cannot see them, and if it has mass, kind of virtually exists. And also the rate of expansion of the universe is not as predicted in our model. That means the rate at which the universe expands is much faster than it should be, according to our model. And how can the universe expand faster if only have the matter that we can observe in the observable universe now? And so the physicists hypothesize there should be some extra energy pushing the universe to accelerate, so it will accelerate faster than it should be when our observed matter could not provide as much force to accelerate. And those are open questions to physics right now, and those are the ones that we don't know, and physicists only hypothesize some matter exists and energy exists in order to explain what is happening, what is observed in the universe. But even what we can observe, we even don't understand it. For example, the matter we can observe is much more than the antimatter. That means the matter that have the opposite properties as normal matter. And that means if a electron have negatively charged, then the anti-electron, which is also called the positron, will have a positive charge, and also the proton will have an antiproton that is negatively charged. And those are antimatters. But why we don't see antimatter as much as frequent as matter does? And that is a question that we could not explain with our current theories. So if we have an matter, normal matter, and an antimatter, and the properties of them are symmetric, and we may assume that there are equal amount of them, but what is observed is the normal matter is much more than the antimatter, the amount of antimatter. So this is another reason we study the matter-antimatter out of balance question. And there are even more questions that we cannot answer with our physics model. So we try to build something, and such as the collider, Large Hadron Collider, that will produce some new particles or anything that is new to us that we don't know yet, and we hope to find some new particles that can explain those questions or give an answer to it. So the real reason we build that particle accelerator is because there are questions we don't know, and we would like to answer those by performing some experiment to mimic the conditions of the early universe, which is hypothesized to begin in a Big Bang, and the Big Bang is all matter and energy emerges from a point, and you can imagine they release all at once, so the temperature and density is very high, and also the energy of the particles is extremely high, and we want to simulate this energy in our particle accelerator so we can know more about how the universe begins and how it will evolve, and will it ever end, or what is happening to all of the physics we know right now, such as quantum mechanics is describing a wave to be like a particle, so something could have both a particle and a wave property simultaneously. And relativity is explaining the curvature of space-time, which causes effects like ring congestion and time dilation. And those two theories are the most accurate theories of our universe, but they don't fit each other, and we don't know why that is the case. Maybe we are missing something that we can find the answer in a particle accelerator. So the particle accelerator or Large Hadron Collider can answer many questions that the modern physics have, and may provide us clues to why the universe behaves in the way it does today. And you may think this is only an experiment in physics to understand more about the universe, but in understanding more about the universe, we know more about the world around us, and therefore we can use the knowledge to build some technology that is useful to us, and those technology eventually will benefit human, and if we use it in a correct way, and in that case it will make our life much more convenient. Like if you compare to the last generation, they if there are a huge change from the last century, from the discovery of electricity and modern theories like relativity and quantum mechanics, and those theories actually changes how the world look right now, and they are all theories from some experiment, like this particle colliding together. So the result of the collision can inspire physicists nowadays to make some theory about the universe, and if the theory turns out to be correct, it will benefit humanity and also improve our quality of life. So the Large Hadron Collider actually benefits in both worlds. For physics, we may discover more knowledge from this collision experiments, and for normal people that may not know physics, they can also benefit from the technology arises from the knowledge we gain from the experiments. So it will improve their life and make our life even more convenient. So in terms of scientific, the aspect of scientific, and also social aspect, and both aspects will benefit from the experiment of the conducted in the Large Hadron Collider. So whether it is useful to you or not, it cannot be determined, since technology may need time to develop, so it may not directly benefit you or this generation, but it could or may benefit our next generation and even the generation after that. So in terms of evolution of the human race, performing such experiment would be a pushing in humanity in a positive sustaining way, so we can sustain our human race relying on the technology we gain from experiment like this. And that is for now. And if you want to know more, you can reply to me in below the video, and I may improve and add more content to that. And if you think, if you don't listen, if you have any problem in listening my presentation, you may speed up the video and listen carefully. So because I am not exactly fluent at this language, so you may need to adjust or know about that. So that's the end for now. If you have more questions, you can reply after